Okay, so we want to use the definition of the Taylor series to find the first four non-zero terms for the series for cosine x centered at, this needs to say centered at c equal to pi over 3. Okay, so let's first start with the definition for Taylor series. That's the sum from n equals 0 to infinity of the nth derivative of the function f evaluated at the center c divided by n factorial times x minus c raised to the n power. Okay? So what do we really need to calculate here? Well, really what we need to figure out is what this is. Okay? So let's start with n equal to 0. Okay, so f 0 of c, what is c equal to? C is pi over 3. And then over 0 factorial, x minus pi over 3 to the 0. Okay, that's the first term. Second term, f prime pi over 3 over 1 factorial, x minus pi over 3 to the 1. Okay, that's another term. How many do we need? We need 4 non-zero terms. F double prime pi over 3 over, let's see, 2 factorial x minus pi over 3 squared, and then f triple prime pi over 3 over 3 factorial x minus pi over 3 cubed. Okay? And then if we need to go on further and do more, then we will. That would be the case if I like plugged all this in and then, that maybe got me 0 and then that term just drops out. And that, because what we're wanting 4 non-zero terms. Okay, so we'll just, whatever we decide we need to do, that's what we'll do. Okay, so I need to figure out what F0 is. Okay. So this is what? Well, when I take the 0 derivative, that's just the function f evaluated at c. So what is that? That's cosine of c. So this is cosine of pi over 3. The cosine of pi over 3 is equal to 1/2. Okay, that's just one of those things you got to know. All right. So this first piece here, this gets me 1/2. All right, so I get what? I get 1/2 over 0 factorial, which is 1. So I'm working through this first thing, right? This thing raised to the 0 power just gets me 1. So this is just 1. All right, the next one I need to figure out is f prime. So what's the derivative of cosine? The derivative of cosine is negative sine. And so f prime of pi over 3, this equals negative sine of pi over 3, which is negative square root 3 over 2. Okay, negative square root 3 over 2. So I'm going to put negative square root 3 over 2 over 1, and then x minus pi over 3 to the 1. Okay, 1 factorial is just 1. 0 factorial is just 1, right? Okay, let's do double prime. So now we've gotten these first 2 non-zero terms completed, and we'll come back and simplify in just a second. So let's do f double prime of x. The derivative of negative sine x is negative cosine x. So f double prime evaluated at pi over 3. What is this equal to? This is negative 1/2. Okay? So negative 1/2, right, divided by 2 factorial, which is 2. X minus pi over 2, or pi over 3 rather, to the 2. Okay? So that takes care of this term here. So now we just have one more term to get. So f tripled prime of x, the derivative of negative cosine is what? It's sine of x. So f triple prime pi over 3 is equal to the sine of pi over 3, which is square root 3 over 2. So this is square root 3 over 2 over 3 factorial is 6. And then I have x minus pi over 3 raised to the 3. Okay. So what I've done here is I've calculated the first 4 terms. What are those first 4 terms? Well, I can simplify this. Okay, and this is how you'll write your answer. The first 4 non-zero terms of the series for f of x equals cosine x at centered pi over 3 are what? Well, the first one is a half. The second one is negative square root 3 over 2 times x minus pi over 3. The third one is negative 1/4. Okay. X minus pi over 3 squared. And the last one is, looks like square root 3 over 12 x minus pi over 3 squared. Okay. So to write out the nth term of this one, that would actually be kind of challenging, but definitely doable. What I might notice here, like, so when n is, well, I guess when it's odd, okay, when it's, this would be n equal to 0, n equal to 1, n equal to 2, n equal to 3, right? So when n is odd, look at that. You'll see how I've got this factor of square root 3 over 2. And when n is even, I have this 1/2 thing. What's the difference here? One of them's positive, one of them's negative, so I have a sign switcher there. And then over here on this one of them's negative, one of them's positive. I have a sign switcher there. So what's really going on? I could split this up into 2 infinite series, one where I put the even terms together and one where I put the odd terms together, and I could figure out, you know, what this would. Now that's pretty complicated, and you might have a homework problem in which you have to do that. It's doable. It's pretty challenging, right? So what I want to do is I want to give you some formulas that hopefully are going to make your life a little bit better. Okay, maybe just a little bit, right? And so these formulas are for common transcendental and rational functions that you might run into, right? And these are the Maclaurin series for these particular functions, all right? So these are Maclaurin series for the given function. All right, so we have a Maclaurin series. Remember, that's where we're centered at x at a c equal to 0. So c equals 0 for the Maclaurin series. So we have a formula for e to the x, which is x to the n over n factorial. We've got a formula for sine x, cosine x, the natural log of x. Okay, sometimes this natural log one, I think in your book, this is just one I found online. In your book, they do the natural log of 1 plus x. And when they do that, this just becomes x to the n over n. Okay, so that's your difference there. your series still looks like this here, okay? But that's, they just put the +1 there. This one, for whatever reason, they didn't do the +1. So it's okay, it's still the same thing. You've got your geometric, right? X to the n, where your a here is 1. Common ratio is x. This one is binomial expansion formula here. A little more complicated, but definitely doable. Okay. This one here, arc tangent, pretty cool, interesting one that you might run into at some point in the future. All right, so from this table, so using the above table, obtain the Maclaurin series for f of x equal to x squared sine 3x. Okay, x squared sine 3x. Now, if you didn't use the above table, what you would have to do is just mathematically compute it out, which would be rather challenging because if you remember the definition, 0 to infinity, f nth derivative evaluated at 0 over n factorial x to the n. That's the Maclaurin, right? So you'd have to take derivatives of this. Now, the first derivative, you'd have to use a product rule to do it. But then that next derivative, you'd have to use a couple product rules, a product rule and a product rule, and a product rule and a product rule and a product rule, and all this goes on forever and ever, the more derivatives that you take. So it's kind of a nightmare. So you want to use this to your advantage. What key function do I see in here? I see my sine function. So what I'm going to do is I'm going to, ooh, that is not a highlighter. So I'm going to take this and I'm going to use this to my advantage. Okay, so what do I know? So sine of x is equal to what? Sine of x is the sum from n equals 0 to infinity of -1 to the n, x to the 2n plus 1. Okay, let me move that over just a little bit. So 2n plus 1 over 2n plus 1 factorial. Okay, what do I want? I don't just want sine x. I want sine 3x and then multiply by x squared. Okay, so maybe first what I'm going to do is I'm going to multiply by x squared. So I'm going to multiply by x squared. So let me just copy this down here. Duplicate. So I'm multiplying by x squared. That means I'm going to multiply this by x squared. Okay. Now, distributing in here, I can do this. This is a constant. It can come in. Okay. Multiplying just like if I had like 3 times, 1 plus 2 plus 5. I can distribute the 3 in to that sum, right? It's the same idea. I could distribute my x squared in. So what does this become? This becomes sum n equals 0 to infinity. I have -1 to the n. X squared times x to the 2n plus 1 over 2n plus 1 factorial. Things that are the same base, what do I do to the exponents? I add them. So this becomes 0 to infinity, -1 to the n, x to the 2n plus 3, okay, over what? 2n plus 1 factorial, right? Now, what else is going on here? What else is happening? Well, let's see if we can figure it out. Well, this right here, okay, this is x squared sine x, okay? What do I want? What do I want? You know what? I think I've made a boo-boo here, all right? I think I want to work on the inside argument first. Now, it may be that this doesn't matter, but maybe it does. Okay, so let me back up, all right? So this is what happens when everything's done on the fly, right? So let's back up and see if we can't work this starting from the inside. Okay, so starting with the inside of the argument. So let's convert this sine to sine of 3x. Okay, so if I convert this now, what happens? This becomes 0 to infinity, -1 to the n, x to the 2n plus 1 over 2n plus 1 factorial. But instead of having an x here, what do I have? I have a 3x. Okay, I have a 3x, all right? So what is this going to do for me? Well, this is going to give me n equals 0 to infinity, -1 to the n, and then I have 3 to the 2n plus 1 times x to the 2n plus 1. Okay, I just split them up in here. Both of those, they're multiplied together, raised to the 2n plus 1, over 2n plus 1 factorial. Okay? 2n plus 1 factorial. Now, I want to multiply this whole thing. So let's copy this. And let's copy this. Okay. So I want to multiply by x squared. And we're going to use the same technique we did just a second ago. I'm going to multiply by x squared over here. And so I'm going to bring the x squared into the summation. And so I get -1 to the n, 3 to the 2n plus 1 over 2n plus 1 factorial times x squared times x to the 2n plus 1. And so this is series n equals 0 to infinity, -1 to the n, 3 to the 2n plus 1 over 2n plus 1 factorial times x to the 2n plus 3. Okay? So this right here is my Maclaurin series for f of x equals x squared sine 3x. It's a shortcut to do something that's really complicated. I mean, is it possible to figure this out? Yes, you could figure out this an term, but you need to have some mad algebra skills to do it. Okay, you've got to really be salty with your algebra skills. All right, you gotta really know what you're doing. Can you do it? Yes. But is it easier using the shortcuts? Absolutely. And here's the way I think about this, and it's kind of goofy. Okay, so when I look at these here, I think about the sine function. Okay, with sine, this function is odd. Okay, this is an odd function. So that's why I think 2n plus 1, that produces an odd number, right? Well, what do you know about cosine? Cosine is an even function, okay? Cosine is an even function. An even function, this 2n, I multiply 2 times a number, I get an even number, right? So that's an even function. So that's how I remember that. And the exponent on the x is the same as what I put in the factorial. And both of them have the sign switchers, so that's kind of how I figure it out. Now, one one thing that's very interesting, okay, there is a way that e to the x is related to both the sine and the cosine. Okay, it's really interesting, and if you're interested, you can Google how is e to the x related to sine x and cosine x, right? You can kind of see, you look at this, the e to the x, when you're looking at all the even terms, x to the fourth over 4 factorial, what's going on there? It looks like that's all of these terms right here in the cosine, right? And then all the odd terms, okay, x cubed, x to the fifth over 5 factorial, that looks like all of these terms in the sine, right? The only thing difference is the sign switcher, okay? So there's a way that the sine plus the cosine is related to the e to the x. Very, very interesting properties going on there, okay? And you might be getting into something, right now is a little bit over your head, but in the future, potentially you could start talking about Fourier transformations, and basically you can take any function and represent it as sines or cosines, okay? So pretty interesting when we're talking about sound wave applications and making different amplitudes. It's a pretty interesting subject, okay? So log, there's just really not a clever trick I have to help you memorize these. This one here, that one for sure, like you gotta know that one. This one pops up all the time. You're going to use that one probably the most out of all of them. Arc tangent, tan inverse, that one pops up a little bit. So, just get it memorized or have it written down somewhere you can reference it, and you have some starting place to help you figure out what the Maclaurin series is. Okay, so let's stop there, and then I'm going to do one short video on how to find the sum.